A team of engineers in China just made a small stack of chips beat a full-size graphics card by 149 times, and they did it using light instead of wires. This is not a rumor or a marketing claim. It is a peer-reviewed result out of Peking University, and it exposes a weakness in every AI chip built today. The story is not about China replacing Nvidia. It is about something far more important hiding underneath that headline number. Every AI chip sold today is judged by one number: teraflops. That number tells you how fast a chip can do math under perfect conditions. It does not tell you how much time that chip spends doing nothing, just waiting for data to arrive. This waiting is called the memory wall, and researchers say it is the biggest hidden problem in modern computing. A graphics card can have thousands of cores ready to work, but if the data cannot reach those cores fast enough, most of that power sits idle. The team at Peking University decided to attack this waiting problem directly instead of building a bigger chip. They took a neural network with 5 layers and split it across 5 separate FPGA chips. An FPGA is a chip that can be rewired for one specific job instead of running general code like a normal processor. Each FPGA was permanently assigned one layer of the network. The first chip only ever handled layer 1. The second chip only ever handled layer 2, and so on through all 5 boards. Instead of connecting these chips with normal copper wires, the team connected them with light. Each FPGA got its own silicon photonic transceiver, a small device that turns electrical signals into pulses of light and back again. Each transceiver could move data at 400 gigabits per second. The light traveled using 4 different wavelengths at 1270, 1290, 1310, and 1330 nanometers, all packed onto the same fiber at once. These light signals pass through a 16 by 6 optical switch, a piece of hardware that can send light from any input to any output without slowing down or losing signal. Here is why light mattered so much. A normal network switch has to check, hold, and schedule every packet of data before sending it forward. That takes time. An optical switch skips almost all of that. It is closer to a clear path for light to travel straight through. This let one chip finish its part of the work and pass the result directly to the next chip almost instantly, with barely any delay. Think about a factory line building a toy in 5 steps. If one worker does all 5 steps alone, the next toy cannot start until the first one is finished. But if you split the steps across 5 workers, and each one hands off the toy the moment their step is done, all 5 workers stay busy at the same time. Finished toys start coming out one after another with no gaps. This is exactly what happened inside the optical chip system. Now here comes the number that shocked people. The team tested this system on a real task, cleaning noise out of small clothing images from a dataset called Fashionist. Each image was only 32 by 32 pixels. They ran 1,000 images through the system in batches of 10. The full 5PGA pipeline finished the entire job in 105.16 microseconds. To put that in perspective, a microsecond is 1/1,000,000th of a second. Based on the theoretical limit of the hardware, a perfect version of this system would have needed about 99.6 microseconds. That means the real system hit close to 94.7% compute utilization, an extremely high number in a field where losing 30 or 40% of performance to overhead is considered normal. Then they ran the exact same task on a commercial GPU with 372 CUDA cores and a theoretical peak of 16.96 teraflops. On paper, that GPU had more than 8 times the raw compute power of the 5 FPGA system, which only reached 1.969 teraflops, but the GPU took 15.643 milliseconds to finish the same job. Compare that to 105 microseconds on the Lightlink system, and the difference comes out to almost exactly 149 times faster. A system with roughly 11.6% of the GPU's theoretical power beat it by nearly 150 times. That is the number that spread everywhere, but the real story is what caused it. The GPU lost because of overhead, not weak math.
Inside a secured facility in Shenzhen, something impossible just happened. Huawei, the company written off by sanctions, confirmed testing of a homegrown UV lithography machine in early 2025. The machine fills an entire factory floor and generates the exact 13.5 nanometer wavelength needed to etch 3 nanometer chips. When ASML, the Dutch monopoly holder, heard the news in March 2025, their stock dropped 7% in a single day. The experts who said this would take 15 years are now scrambling to explain how China did it in just 5. Let's be clear about what we're talking about. Extreme ultraviolet lithography is not just another manufacturing tool. Each ASML machine costs over $350 million, weighs more than 180 tons, contains 100,000 precision parts, and took 20 years to perfect. These machines use light with a wavelength measuring just 13.5 nanometers to print circuits 30,000 times thinner than a human hair. Without UV, making chips smaller than 7 nanometers is essentially impossible. ASML was the only company on Earth that could build these machines. Until now. Back in 2019, the Trump administration hit Huawei with sanctions that cut them off from American technology. ASML, under intense pressure from Washington, stopped shipping UV machines to China. Huawei's manufacturing partner, SMIC or Semiconductor Manufacturing International Corporation, was stuck using older Dove technology that maxes out at 7 nanometers. Western analysts were unanimous. Without UV access, China's chip dreams were finished. ASML's CEO said in December 2024 that China was still 10 to 15 years behind. That timeline just collapsed. China didn't try to copy ASML. They invented something completely different. Instead of ASML's laser-produced plasma that fires 50,000 pulses per second at microscopic tin droplets, Huawei developed laser-induced discharge plasma, or LDP technology. The method is simpler. Vaporize tin between electrodes, zap it with high-voltage electrical discharge, and you get plasma emitting the exact same 13.5 nanometer wavelength. But here's the critical part. It's cheaper, more compact, and bypasses hundreds of ASML patents. On January 3, 2025, Harbin Institute of Technology officially announced their breakthrough. Professor Zhao Yongpeng's team successfully developed an UV light source producing stable 13.5 nanometer radiation. Their discharge plasma extreme ultraviolet lithography light source project won first prize at the Heilongjiang Province Science and Technology Innovation Competition. The system achieved power levels between 100 and 150 watts by mid-2025. The technical specs are remarkable. A research team led by Lin Nan, a former ASML engineer now at Peking University, published results showing a conversion efficiency of 3.42%. That might sound low, but ASML's research arm Arcanel only achieved 3.2% in comparable experiments back in 2019. These aren't wild claims. The paper was peer-reviewed and published in March 2025 by Chinese Laser Press. This is a coordinated national effort. Harbin Institute of Technology developed the light source. Chengchun Institute of Optics created high-precision reflective mirrors with accuracy down to 0.2 nanometers, reportedly surpassing lenses jointly developed by ASML and Germany's Zeiss. Shanghai Microelectronics Equipment Group, known as SME, handles overall integration. Huawei and state-backed firm SciCarrier coordinate more than 3,000 researchers across lithography, deposition, and etching equipment development. The Chinese government committed $37 billion specifically for UV lithography development, with additional investments in semiconductor self-sufficiency totaling over $150 billion through 2025. The prototype machine reportedly became operational in early 2025 at Huawei's facility in Dongguan. According to multiple industry sources, trial production is scheduled for Q3 2025, which is right now. Mass production targets 2026. Reuters confirmed in December 2025 that China secretly completed an UV prototype in Shenzhen. The machine is functional, generating extreme ultraviolet light, and testing is already underway. Initial tests confirm the machine can achieve precision required for single exposure patterning at the 5 nanometer node. Why does 3 nanometers matter so much? The numbers tell the story. A 3 nanometer chip can pack nearly twice as many transistors into the same space as a 7 nanometer chip. This doubles computing power while cutting energy consumption by up to 30%. Your smartphone could run advanced AI models entirely on device. The West's lead in this technology has powered everything from Nvidia's dominance in artificial intelligence to Apple's iPhone empire. The market reaction was immediate when news broke about Huawei's Ascend 910C chip reportedly matching performance of Nvidia's H100. Nvidia lost $127 billion in market value in a single day. Nvidia is now publicly warning investors about Huawei's AI chip gains. SMC, the Taiwanese chip giant, lost $180 billion in market. The geopolitics are shifting fast. China accounts for 40% of ASML's global sales, but if Huawei and SMIC succeed with domestic UV, that remaining 20% could vanish entirely. ASML's monopoly, held for decades, is crumbling. Xi Jinping made semiconductor independence a national security priority comparable to food security or energy independence. Let's be realistic about challenges. Current production yields are around 20 to 30%, far below the 70% needed for commercial viability, and nowhere near ASML's machines that achieve yields exceeding 90%. Goldman Sachs released analysis stating China's homegrown lithography machines remain approximately 20 years behind global standards in overall sophistication.
On April 28, 2025, Nvidia's stock dropped 2% in a single day. No crash, no earnings miss, no scandal. Just one report that Huawei was testing a new AI chip. A chip made inside China under brutal US sanctions, using technology that was never supposed to work at this level. That one report wiped out billions in market value before lunch. So what exactly is Huawei building, and should the US tech industry actually be scared? Let's start with how we got here. Back in 2019, the United States hit Huawei with devastating sanctions. The crown jewel of that strategy was pressuring ASML, a Dutch company and the only manufacturer on Earth of extreme ultraviolet lithography machines, to stop all exports to China. These machines cost between $150 million and $380 million each. They weigh 150,000 kilograms and need 250 shipping crates just to transport. Without them, making chips smaller than 7 nanometers is considered nearly impossible. Washington was confident. They said China would be frozen at 2018 technology for at least a decade. Then, August 2023 happened. Huawei released the Mate 60 Pro smartphone. Western analysts tore it apart looking for the trick. There was no trick. Inside sat a 7-nanometer Kirin 9000's chip manufactured by SMIC, China's largest chip maker, using older deep ultraviolet lithography equipment and a technique called quadruple patterning. Where ASML's UV machines need only 9 steps to create a 7-in-EM circuit, SMIC's approach requires 34 steps. One engineer described it as painting the Mona Lisa with a house painting brush. It's slow, it's expensive, but it works. Here's the brutal reality though. SMIC's 7-in-ear production costs 40 to 50% more than what TSMC in Taiwan charges for the same node. TSMC achieves yield rates above 90% on advanced chips, meaning 9 out of 10 chips coming off the line are usable. SMIC's 7-in-EM yields sit between 60% and 70%. Push them to 5-in-EM and those yields collapse to 30 to 40%. That means more than half the chips they produce are trash. But China isn't running normal business logic. Beijing has poured over $150 billion into semiconductor development since 2014, with another $300 billion committed through 2030. Government subsidies alone covered 87% of SMIC's entire operating profit in 2024. This is a state-funded technological marathon where profit is irrelevant and progress is everything. Now let's talk about the chip everyone is watching. The Ascend 910C, which began shipping in April 2025, delivers around 780 to 800 teraflops of BF16 performance. Compare that to Nvidia's H100, which delivers 2,000 teraflops. That's roughly 40% of Nvidia's raw power. Not equal. Not close, but real, shipping, and scaling fast. Huawei plans to ship over 700,000 Ascend units in 2025 alone, with production hitting 1.6 million dies by 2026. The next chip, the Ascend 920D, is what spooked Nvidia investors. Huawei claims it will match or exceed the H100 in specific workloads. Independent verification doesn't exist yet, but the architecture is using a quad-chiplet design with bridge-style interconnects, and that's not marketing fiction, that's real engineering. But raw chip performance isn't actually the most important part of this story. The part nobody talks about enough is the 6G patent war. Right now, Huawei holds 15.7% of all global 6G patents, more than any single company on the planet. China as a whole controls 42% of global 5G standard patent declarations.